Okay, thank you. So, hello everybody. So today we are going to talk about some local kernel debugging on Windows. And you know we are some researchers at Society and we like chilling, and in our spare time we like reading the Intel manual, and we found some really cool feature which is called branch trace flag. In fact, if you activate some model-specific register on your CPU, you will be able to step on each branch taken by your processor. So it's really cool. And in fact, it's almost implemented in Windows, but it doesn't support the new family of CPU nowadays. If you use AMD 64, it's supported on all family. So that's it. And we found another cool feature which is called branch trace store. You just register a memory region where all the branches taken by your processor will be stored. So that's it. And there is another function inside NTOS kernel which is called VF initialized branch tracing, but she's totally bugged and she doesn't work. So we wanted to be able to use these features on Windows and try to fix it. So how can we achieve that? So we look at some options. We start looking at WinDBG, which is a debugger offered by Microsoft Windows. But when we looked at the scriptability of WinDBG, we were, oh shit, it's gonna be a pain in the ass to use this. So we started to look at how WinDBG works, yes, and think about why not drawing a local kernel debugger. So today we are going to talk about Windows local kernel debugging, how DBG engine works, and some Python Kung Fu with Clément, and of course some demo. So, why will you use kernel debugging? So every day you are reverse engineering NTOS kernel or some driver to find vulnerabilities or to find bugs or whatever. You try to understand hidden features. There is a lot in Windows. Every second Tuesday of each month, you study the patch Tuesday, so you fire up bindiff, and then you fire up WinDBG to be able to debug the patch and create a proof of concept, or you are a bad guy and you want vulnerabilities. So yeah, that's it. And if you are a driver developer, you will use a kernel debugger, and etc. So Windows offers a few options for kernel debugging. You can do it via the network. Of course, it's encrypted. The client have to exchange a key with that. You can do it with USB, a serial cable. You always use this option when you debug virtual machine, and of course, locally. So this is the subject of today. So locally, what does it mean? It means that the debugger is running on your computer that you are actually debugging. Of course, you won't be able to put breakpoint or your machine, your computer will freeze. But what you can do is dumping the memory, virtual or physical. You will be able to dump the data structure of your processor like the GDT or IDT, internal structure of Windows like the process list entry, and of course, you can modify the memory. So you can read it and write it. And you can read and write also input-output and model-specific register. And in our case, it was cool. So you will be able to enable hidden features and fix bugs, you will see. Microsoft Windows offers a tool called WinDBG, and you have an option to debug your kernel locally, and that's it. So for the prerequisite to use that, you will have to modify the boot start option. So of course, you have to be administrator of your machine, and if you modify the boot option and you use secure boot, BitLocker, sorry, it will be learned that you have modified the boot option. If you modify the boot option, a global variable named kd-debugger enable will be set to 1. And of course, there will be a string in some register key. And you can do it using bcdedit or msconfig if you prefer to click. Okay, so how it works exactly. WinDBG, in fact, use a DLL named dbgeng.dll. Of course, it's debugger engine. It provides interfaces to communicate with your target, like a computer you want to attach to a computer for reading his memory, setting breakpoints, etc. So we thought, yeah, why not using this DLL to write our standalone local kernel debugger? And go fuck yourself, WinDBG. dbg.dll, in fact, if you open it in a PE Explorer, you will see that it exports a few functions, and there is only one interesting, which is debug create. It takes at first parameter an interface ID, and the second parameter is just the output of your interface com that you want to create. So you can request a comma object, and there is a main object which is called edebug client. With an edebug client, you will be able to request other interfaces. The first one is edebug control. You will be able to control your debugger, like setting breakpoints, resume, etc. Edebug symbols. It's about all the symbol stuff offered by Microsoft. So at an address, you will know, yes, this is this function, or if I want to dump the structure, an internal structure of Windows, you will use the symbol. And edebug data space for all the read and write operation on virtual, physical, input-output, MSR, etc. So by dissecting the documentation inside the CHM, it's a HTML compressed format of Microsoft, we can find an attached kernel. It takes as first parameter a flags and a connect options. But when we went inside a defined file, dbgeng.h, we found a hidden flags that were not documented on the online documentation. It was called debug_attach_local_kernel. So we thought, okay, let's try to put this flag and see what happens. If we try to call this method, we will end up in a function named local, inside the com object, local live kernel target info init driver. So we thought, what? There is a driver. So this function, in fact, will check if your process name is WinDBG or KD, just by using the API get module name. And if true, it will extract a signed driver, which is called kldbg.sys, driver.sys, sorry, from the binary resource with the name 777 and type 4444. In fact, this driver just creates a device for the communication from user land to kernel land. And it's just a wrapper around an exported function of NTOS kernel, which is called KD system debug control. So you just send an IOCTL with the code 22C007, and it will call this exported function of NTOS kernel. And you will be able to access all the features offered by WinDBG, in fact. So this function, in fact, checks if you are in debug mode, of course, and you will be able to read-write to input-output, to memory, physical, virtual, MSR, on the database, so whatever you want. But we have found a little bug inside two functions. When you were reading or writing to some I/O, all the addresses have to be aligned. So it's pretty stupid. So we will see that we had to patch it. So this was one of the bugs we had to fix. So if you want to create a local kernel debugger, it's really easy. We just grab the DLL, dbgeng.dll. We just put resources in our processes, like the driver, and we just add other resources like dbgeng.dll, dbghelp, and cmaserve for all the symbol stuff. And we don't need to install anything, and we have a local kernel debugger. So we just name our executable windbg.exe or KD, or we can hook the get module file name API from kernel 32. We enable some tokens, so we can load the driver. We check that we are, of course, in debug mode. We will load the dbgeng.dll, create the com object, attach kernel, and then just wait, and we will be able to do whatever we want on our machine. So that was the C part, but you know, we rely on compilation step, and we don't like that. So now let's talk about Python.
Yeah, so we are able to create a local kernel debugger, which is pretty cool, but yeah, I'm really not a fan of compilation. It's like a really complex tape, and I really want to have the loop, the Python loop with the interactive interpreter, and that the interactive loop to do kernel debugging is pretty fun. So let's try to implement the same thing in Python. So what are the problems we have and what do we need? We need to be able to call COM interfaces from Python. We need that get module file name w return when dbg.exe, and we need to embed kldbg driver.sys as a resource. We won't take the easy path, which will be that could be yeah, we take python.exe, rename it WinDBG, and that's okay, and we can add the resource. It's like cheating, and what we want is be able to use vanilla Python, so any Python installation, and be able to perform local kernel debugging from any Python installation. So what will we use is the ctypes module from Python, which is the module for the interface with C, which is like my favorite Python module. Yes, I have a favorite Python module. It's pretty sad, but it's cool. And we will do some import address table hook in Python. So we'll begin with the simplest part, which is calling COM interface from Python. So as you can see, we have a function which is set symbol path, and we just set the symbol path. You can see that it takes one parameter, which is a string, the path, and return an hash result, which is the return type of every COM function. And if you look at it, in the real convention is like you have a p void and the string, and the p void is your COM interfaces. It's exactly this call, and the p void is your this. So how do we do that in Python? And it's like 3 lines of Python, 2 lines in Python, because of the ctypes module, which handle everything for you. All you have to do is declare a new type of function, a winfunc ctype. It's a Windows function, so the callee cleans the stack, and that's it, which return an hash result and take a string. And to that type of function, you call it with 2 parameters to tell him it's a COM interfaces. The 41 is because set symbol path is a 30 second entry, but you begin with 0. And set symbol path is the name of the COM function. Why we need both of them? Because if you only give it 31, it will try to create a function at address 41, and jumping on 41 is like a bad idea. So with those 2 parameters, ctypes knows that it's a function that takes a COM object, and we call the good entry in the v table. And after that, you have your function, and you call your function with your COM object and, of course, the string. And if you want to abstract stuff, because abstractions are cool, you can use the partial, tools partial or some other abstraction to completely hide the this call and perform the this call behind the back of the user. And you have like a standard COM call in Python. So the easy part is done. We can do COM call in Python. So let's go with the IAT hook in Python. So what do we need to perform IAT hook and IAT hook in Python? We need to find the PEB, the process environment block, to know where are the function and the address of the import table in our modules. And we need to perform some PE parsing to find the export and the import. We need to hook it with a stub able to call some Python code. Because we want hooks and callback in Python. It will be really too easy to have native code, so we want Python as a callback function. For that, we need 2 things. We need to be able to call native code from Python and call Python from native code. So the first one, ctypes magic, once again, it's like pretty easy. The first line, it's the code to get the PEB address on 64 Windows. So the PEB in 64 is at GS60. So here we have the hexadecimal for the code, which is move RX GS60 ret. We declare once again a function, a ctypes function that just takes no argument or return a p void, and it's our func type. And we write our code, our native code, somewhere. So this function hide an allocator that allocate pages writable and executable. We write our code at a given address, and we create a function at this address saying, hey, this address is some native code that take no parameters or return a p void, and we have our functions that we can call as we want, and we can perform really simply native execution in Python and get our PEB. For the other part, how can we call Python code from native execution? It's also a ctypes feature that is like very cool, but I never seen anybody use it, but maybe I'm not good at looking. So you can create your own callback that do whatever you want, that takes 2 parameters. Once again, you create a winfunc type, which return a uint and take 2 uint. And after that, all you have to do is like, hey, my func type is my Python callback, and it will create a secallable object, which is a Python object. And this Python object hide in itself a stub, which is a native stub able to be called from anywhere and call our Python callback. The fact we have 2 problems. The real address of the stub is hidden. You can see it from the Python. So you need some little tricks to extract this address. And this stub is not enough for our IAT hook, as we need to prepare the thread to call Python code, because we are absolutely not sure that our code will be called from the same thread. And every thread that called, any other thread that called Python code need to be prepared. So we will manually create another stub that will call the setType stub. So what does this other stub do? It will need to call the PyGIL state answer before the ctype stub. The GIL is a global interpreter lock. It's a big lock in Python that allow you to do thread in Python. And you need to release it after your thread, after your hook. But the problem is that the setType stub is expect a state on the stack to parse the parameters and create the parameters. So we need to pop the return address and save it somewhere else, not on the stack. And we need to save our register and our state, and also not on the stack. After that, all you have to do is hide all the magic with decorator, because decorator are cool. You handle all the level magic in your decorator. You create a Python function calling your real API, because half of my hooks call afterwards the real function. And we call our hook with the original arguments and the real API for other call. For example, we have a callback. Which is a hook that return a void pointer. So it's exit, but we need to give it a type, so void pointer, and which takes a culong. And the parameter that takes our hook is the x, so the ulong, and the real function. And you can do whatever you want it. So if x is 42, you can real exit, or you can make exit return. And with this callback, you can just take the IAT entry of your exit process and set your hook. As a bonus, we are able to generate specialized callback decorators for function with non-arguments, because we know that the exit process callback take a ulong. So with this information, we can generate the good callback decorator, and that's all. So what is the application to Debugger engine.dll? So we see that the local live kernel target info init driver checks the name of the current process. So we will hook get module file name. So with our emulate WinDBG name. And if the H module is not known, we call the real function. And what we will do is we take the LP file name, so the destination address, we cast it to void to get the real address. And at this address, we will write just say.windbg.exe. and it's like a messy act to write with C types somewhere, but we just return C // when dbg.exe. And we also need to embed KL dbg driver.sys as a resource. So what we do is we create a resource from a path on the hard drive. And for example, the load resource hook will have its own dictionary of loaded resource, of opened resource, and we just load the resource. And the code loading the resource is like pretty simple. We open the file, we get the address of the open file, and we return the address. The only problem we have is that we are like having address of Python objects which are not referenced anymore, so we have problem with the garbage collector. And I have a lot of, I had a lot of bug with the garbage collection. So when you do things like that, you need to have some list that stores the Python object, because if you have a pointer that you return on a Python object that is garbage collected, it's a seg fault. So yeah, you really need to be to know that there is garbage collection, how it works, and after that, it's like a wonderful world. So with that, what can we do? We have a dbg interface module. We have a local kernel debugger object. We create a new local kernel debugger, and we have everything we want. You can get the symbol of get the offset of a symbol, for example, case system startup, and read virtual memory from this address, and it works. So, for example, here we have a Python 64 for our test, because you cannot do local kernel debugging from a syswo process. So on a 64 kernel, you need a 64 Python, and obviously on a 32 process, you need a 32 Python. So that's the only problem, and you can do anything with that. So now it's pretty cool. We have local kernel debugging on Python, but as Samuel said, we have some bug, and there are some features we really want, and that aren't available, so we will try our best to change that. So let's try to level up. So we cannot perform non-aligned I/O because we have two functions that are like really buggy. We are unable to allocate kernel memory, and allocating kernel memory is pretty cool. And we are unable to call custom kernel function, and calling everything anywhere in the kernel is like pretty useful too. So we didn't want to disable secure boot, so we didn't want to rely on compilation step. So we don't want to have another driver that we will load afterward. It's like no compilation at all. I hate it. So what we will do is that we will use the KL-dbg driver feature to upgrade itself. So we are able to write in virtual memory. We are able to write in physical memory. We have a driver in memory. Why not write on the driver memory to change its code and upgrade it in the kernel memory? It's like pretty simple. All you have to do is take the code that handles the EOCTL, and change the execution path to add your own code. So what we have now is the ability to register custom code execution in kernel for a given IOCTL code. With that, we can implement the non-aligned IO call, the call of custom kernel function with arguments, or allocate kernel memory, and why not map it to user land. For example, we have our upgrade driver, and we will add a new IOCTL handler, which this is the number of the handler, okay, and this is our code that we will be injected in kernel and called when we call something with the du mmalloc IOCTL. And the code in userland is pretty simple. All we have to do is like we have our alloc memory function that takes a size, a type, and a tag, just like X allocate pool in kernel. We create a buffer. We take the address of the buffer and we do an IOCTL with our IOCTL code and the handle of the driver. And we return the res.value. And if you try it, we have our KDBG, we alloc some memory with a size and a tag. And if you use WinDBG, you can see that the address returned is a large page allocation with a tag LKD of the good size. So we are able to allocate code in kernel. Something fun I didn't mention anywhere you can have multiple local kernel debugger at once. So you can have 2 Python scripts performing local kernel debugging and a WinDBG performing local kernel debugging. It's not a problem. I don't know if it's useful, but it's not a problem. So now we will try to do some demo to show you that it's not just some useless code and that we can do some things with that.
Okay. So first, I think some of you use WinDBG, and for example, we have re-implemented some useful function, commands, sorry, like IDT, so you can explore all your interrupt descriptor table and see all the symbols, for example. So you will just run the script. Is it running? Okay, cool. So just loading. Take a bit because of the loading of the driver and just there. And we can see that we got all the entry of our IDT, all the virtual address of all the entry and the symbols and all the key interrupt associated with them. You can see that you have all key trap, etc., etc. Okay, next. Okay, shit. Okay, just wait. It's a bit slow to rerun it at each run, but yeah. Okay. So next demo is about exploration of all your PC device. So if you want to fuzz them, for example, or to try them, you can explore them and see what are their ID, and you can send requests to them. Okay. A bit slow now. I think it's because of the VM. Yeah. Okay. Yeah, she was pretty slow. This. Ouais, vas-y. Okay, so we will show you some example of code to show you that it's really simple to use it. At first, you will create your DBG interface. Remonte. Okay, you just create your local kernel debugger, and you got just a Python object to play with it. And for example, we just create a wrapper to read all the PC device, and we just call the read bus data, and we will be able to read data on all the PC bus data. And we just explore all the ID of device vendor ID. So it's, oh, okay, thanks. So as you can see, we are under VMware, and we can see those devices and their ID, and we can explore them to see if they expose mem.io or stuff like that. Okay. Yeah. So maybe some of you know the tool Spike ID. It's a WinDBG extension that offers Python features, but the main problem is it relies on WinDBG, and we wanted to be able to use it as a standalone. So we thought, yeah, it would be really cool to be able to execute our script inside IDA. So let's try it. So it just adds the path of our project inside IDA, and it will just load the local kernel debugger. So of course, it's a bit long. Okay, so, and now we just got the object on our kernel debugger, and we will read the virtual memory at the function ksystem startup, and we can see the opcodes, and they are the same in IDA, so we can check some stuff or write to them. So the next, we will list all the modules loaded on our PC. So we just said NT star, so all the prefix NT, so we can see the base address on NTOS kernel, and the NTFS driver is loaded at this address. And why not exploring the KPCR data structure of Windows, which is all the internal structure of your processor, like the IDT, GDT address, and you can explore them, etc., etc. Okay. So the next demo is about hooking function in the kernel. So we will set up inline hook in kernel to monitor function. So for example, we will set up a hook on NT create file from userland, and just see what the VM do, if you want to play. Okay, and you see all the handles opened by the VM, and you can set up whatever you want. Okay, cool. Yeah. Okay. The last one, so at first we were talking about the PBS, so about a branch trust store, and you have to do it on a physical machine because, of course, a VMware or VirtualBox or whatever doesn't implement this kind of stuff. So we will activate it and see all the branches, all the last 20 branches taken by our processor. So let's go. BSOD or not? Okay. Oh. Okay. Forgive it. Okay, try again. So to enable that, you just need to set up a DS area. Okay, so it's not working. Okay, so we get because we need the symbol to be able to allocate memory for where the CPU will store all the data of the branch is taken, and we forgive to download the symbols of this physical machine. So, but we have a screenshot that we have run the script, and yeah. And you can see all the last branches taking the source and the destination with the symbols, and they come from this and they go to this. So it's pretty cool. And you got the output to user land where they come from. Kernel land to user land, for example. This line, case system service exit. Okay. Okay, cool. So to conclude, local kernel debugging is a really nice feature provided by Windows kernel. We have really enjoyed abusing it. Now we can offer you a really script ability to do kernel debugging. And of course, our code is available on GitHub, so you can download it and test it and play with it. And I think that's it. So thank you for your attention. If you have any questions.
So we got time for a few questions.
So for those that are wondering about IDA, if you know that X-rays are asshole because they just offer a 32-byte process of IDA. Even if you reverse 64-byte file, it's a 32-byte process. So at this time, we are not able to do local kernel debugging of a 64-byte kernel using IDA, just to be clear. But we have a